Um, okay. بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. Assalamu alaikum everyone. So good to see you that you survived first round. So this is the second round, inshallah. Same topic. I hope you did some reading or got some time, just to do some calculations into the stuff I sent you by email. Today, inshallah, we're going to be moving on the same on what you've been working on and moving forward in the same topic. So as usual, let's start just with a recap, and then today, inshallah, we're going to be looking at the mass damper system, and we're going to be analyzing it, trying to understand, just from math, what do we expect the behavior, how it should be, without simulating the system. So this is very important. So the analysis means you just take, pen and paper, and you try to see how the system will behave. And then this is exactly what you should expect if you simulate the system, or if you run it in real life. This is how it should behave. We're going to be doing exactly the same with the flying end-effector dynamics, and we're going to see here the analogy which the Port-Hamiltonian framework. So the power, when you have the Port-Hamiltonian framework gives you, that you can see systems that in principle should be different, right? So the results should be completely different from an analysis point of view, but because of this unified framework of modeling, then you can really see that there's a lot of reusable information, that if you analyze one system in the Port-Hamiltonian framework, it's easy to transfer this knowledge to a different system. And then we're going to be looking at impedance control. So today, inshallah, we're going to be looking at the control of both this mass damper system and the flying end-effector one. So the recap, what we discussed last time was the Port-Hamiltonian systems. It gives you, it was rooted in three domains. The first one was port-based modeling, which was trying to use, so that has this idea of, instead of looking at signals, just unilateral signals that go from one subsystem to the other, we look at bidirectional systems, so bilateral systems. And these, the choice of signals, which are called effort and flow, in the end give us the power that flows through this bond or this port. So all of these half arrows, they correspond to a port, and the arrow that you see here is simply just the positive power convention, right? So the geometric mechanics domain is a domain that represents systems not using coordinates, but in a coordinate-free manner, trying to abstract as much as possible into the standard. When we're studying systems with the standard state space form, x dot is equal to f of x plus g of xu, we have an output equation y is equal to h of x. The geometric mechanics tries to abstract this and try to say that, okay, x, if it doesn't live in Rn, you need to take this into account. So if it's not just the Euclidean space, it has some manifold structure, it has some geometric structure, we need to take this into account. And the third one is the systems and control theory, which, as you all know, so the starting point in doing systems and control is to model the system, write it in terms of differential equation. Then you can start to think about more control and simulation and whatever, or analysis. The Port-Hamiltonian framework, if you combine all of these three domains together, or three different ways of looking at systems, you get this more structure into a dynamical equation. You get, instead of just having f of x and g of x and h of x, you have more structure that correspond to the power, how each one of these subsystems, how each one of these terms play with respect to power. You're going to find that in the end, we have some terms that correspond to energy storage, some terms correspond to energy dissipation, and some terms that correspond to just energy routing, which is taking one energy from one place to the other within the system. Okay, so this is very important. We're trying to decompose one equation of motion into different parts, so that we can really understand what's the contribution of each part with respect to energy. And this is the whole idea of the Port-Hamiltonian framework. And this is how you would see one system just as a bunch of atomic modules that in the end they have something to do with energy. Okay, and this is very general. Okay, you can do this in different domains. And today, inshallah, we're going to be seeing an example which is on the mechanical part. And so this is just, I'm going to skip this part. What we discussed previously is that after you have the different subsystems, you can always interconnect them. This is very important. So after you study each subsystem by itself, you can always interconnect them and make something bigger out of it. This is exactly how we're going to be doing control today. So we're going to be thinking of, so our original system will be a Port-Hamiltonian system. And then we're going to be thinking of the controller also as another Port-Hamiltonian system that's interconnected to the bigger one. Okay. And this is very important because when we're studying the total energy, so when we're studying the closed loop system, which is the controller plus the original system that we had, we can simply just sum up the energies. We can simply just, stack the states, and the resulting Port-Hamiltonian system, which was the combination of the original, okay, so the original one and the controller Port-Hamiltonian system, is another Port-Hamiltonian system. This is a very important property. In finite dimensions, you have that the composition of Port-Hamiltonian systems is another Port-Hamiltonian system. Okay? And this is where this theory becomes very powerful. You can extend this again and again. You're going to be seeing throughout this today, inshallah, in the next lecture, you're going to be seeing how we can do control using this simple, okay, powerful property. And in the end, all of these different modules, you can always abstract them. You can always combine all of the resistive parts into one part, which causes dissipation for the whole system as a whole. You can have one big storage element, then you can have one big external port that corresponds to. You can use this external port to connect this whole system to some other stuff. You can even make this big system bigger and bigger and bigger, and so on. A recap of what we discussed, just as a simple example, that the standard point mass dynamics that you're all used to, which is simply just m psi double dot, is equal to some gravity force and some control force. It's just a very simple equation. No damping, no stiffness. It's just a mass that just it would fall down. And we saw that if you look at this without thinking about energy, you're just losing a lot. But the Port-Hamiltonian system takes the energy and makes it explicit. So you have here the energy function is simply the kinetic. So the total energy, which is the Hamiltonian here, is the sum of the kinetic plus the gravitational potential energy. And the and the gradients of this Hamiltonian function with respect to these different two states is given by the following. And you can always rewrite the original dynamics that we had up there into this form that's in the Port-Hamiltonian form. You can always do this, okay? And you can always find that in the end we have this generic structure. Of course, it might be more difficult. So for example, here in this simple example, J and G, J is always skew-symmetric. G is just the input map. You can have, there's no damping here, so we don't have this R matrix. But in general, you can have the J to be a function of X, the R can be a function of X, and also the G can be a function of X. It doesn't change the structure, doesn't change the energy balance as we're going to be seeing today, inshallah. And this is very powerful. So you can even working with nonlinear systems that have highly nonlinear stuff, it will be very easy to do analysis as you're going to be seeing in today's lecture, inshallah. Our main focus in this course is in this mini course is on the flying end-effector, which was this fully activated hexarotor that we can control all of the 6 propellers to produce in the end a collective wrench. And we said the kinematics part is simply, the rate of change of position is related to velocity. It's not equal to velocity, and this is the main challenge here when working with 3D mechanics, is related to the velocity. And dynamics, the part which is simply just the conservation of momentum. So you have the conservation of angular momentum, the conservation of linear momentum. All of these nonlinear terms are related that you have coupled rotation and translation at the same time. The first ones we call gyroscopic, the second ones we call them Coriolis forces. And then you have the gravity force, you have the control force and the interaction force. And similarly, you have the control torques and the interaction torques. This form of the equations, it can be generalized or it can be rewritten into using you combine rotation and translation into one object that we call the homogeneous transformation. You combine the linear velocity and the angular velocity into some object that we call the twist. And then you have the kinematic equation written like this. And you have the dynamics. You have now, instead of linear momentum and angular momentum, you combine them. You have this generalized momentum, and all of the Coriolis and gyroscopic force, they go into this nasty term, without looking into details. And then you have the gravity wrench, you have the control wrench, and you have the interaction wrench. So the term wrench means generalized forces, which combines torques and forces in the Port-Hamiltonian framework. So if you look at, so this is, again, going back, this is the standard way of looking at the equation, just the kinematics and dynamics. But if you add the energy, if you think about that, this system, it also has some energy. It has total kinetic energy, which is the rotational part and a translational part, and it also has some gravitational potential energy. So if you look at this energy, you can also represent it in terms of the pose and the generalized momentum in this form. And the Port-Hamiltonian dynamics would be represented like this. So forget about the details inside. If you had some time to look at it, this might make a little bit more sense. If not, we're going to be try to do like demystify it a little bit today, inshallah. But just the main conclusion is that you have the J of X part. So the J here is not a constant. It's a function of H and of P of the two states. And we have the G is constant, and we have here two places where we can get a wrench. We can have the control wrench, and we can have the interaction wrench. And this figure on the top right today, inshallah, will be a little bit more clearer when we look at how we represent the system in this form. Now, before jumping into the control part of this complicated system, let's take a step back. Let's go back to a mass damper system, just one system that has a mass and a damper, and we try to analyze the equations, okay, just to see how does energy evolve, okay, with this system. We're just going to make it a little bit interesting. So it's not just a linear system. We're going to be making it a non-linear system. So you see that we have this inertial frame, that the S frame is a spatial frame. And this psi would represent the position of this point mass in this frame. There's no orientation, so it's just I just need one coordinate. So three numbers to represent this system. So x and y and z, for example, or polar coordinates in general. You have a gravity force downward. We assume a gravity, the inverse of the gravity. We assume gravity is downwards, but we have this g vector that corresponds to up. G vector is up. So whenever we say, for example, gravitational potential energy, we say it's mgh, right? So mg in the z direction. The point mass can move, so it has some velocity. We can apply a control force on it, F_con. And whenever it starts to move, it always has some sort of damping behavior. It has some sort of, it faces some wind, and then based on this velocity, you're going to have this damping term. It's non-linear. It's not just, damping. Linear damping, it's non-linear. So the square bracket, so it corresponds to the norm of V. So V is 3 numbers. When you take the norm of it, you get only one number, right? That corresponds to how fast it's going, is the speed, and then you multiply it by a constant B, which is just the damping coefficient, and you multiply by the vector again, V. Okay? So in the end, this is just a vector, 3 numbers. Mg is a vector because G, it's pointing up, is a vector, and F_con is a 3-dimensional vector. So everything here is vectors, and we have here on the left-hand side the rate of change of momentum. This is how you would write it in the standard state space form. You would choose the first state as the position, the second state as the velocity, and you just rewrite it like this. Does this make sense for everyone? Okay. So this is how you would how do you face this, how do you approach the system, and then afterwards you would do analysis or do control and so on. If you would want to look at, for example, what is the energy in the system? But now it's not. If you're doing it in the standard way, this is an extra step. It's not inherent in the formulation. It's just something extra. You can do it or you cannot. Usually, we need to do this analysis if we want to do, for example, stability of the equilibrium points of the system. If you want to do a controller and so on. So this stability analysis is always we do it. You need to choose some sort of energy-like function. But for any mechanical system, we already have something called an energy function, right? So any mechanical system has this kinetic energy. It's moving, and it has potential energy if it has some sort of, either gravity or if you have some stiffness inside of the system. So in this case, we have half mx2 transpose x2, which is equivalent to half mv squared, but just in 3 dimensions. And we have mgh, right? But the g itself can be gravity. Okay, so it can be a vector, and the h itself, this is just a more fancy way to write it because the gravity can be a little bit tilted. The spatial frame itself, you can choose to tilt it, so it's no longer you're not bound to say that z is always up. This is just a more generic way, but in the end, it's equivalent to mgh. Okay. How would you calculate the h dot? The h dot is simply you say I have this as a function. I want to take the rate of change of a function of x. Okay, and x itself is a function of time, because x follows this, differential equation. So x is a function of time. So you just use the chain rule. So the partial differentiation of this function with respect to the first state multiplied x1 dot. But here, because these are vectors, so we need to take, some sort of inner product between these vectors in Rn. So x1 dot is the psi dot. So it's 3 numbers. So x dot and y dot and z dot, for example. Partial h by partial x1 is another vector, okay, the gradient, and then you take the dot product between them. Okay? You do the same for the second state. Okay? Clear? Okay. Then how would you proceed? You just plug in the x1 dot and x2 dot from the dynamics that you had, and you have something like this. The gradient of h with respect to x1, you see, okay, it's mg transpose. The gradient of h with respect to x2 is simply mx2 transpose. Okay, you just need to work that out if it's not clear. And in the end, you reach this equation. Now you need to simplify a little bit. You're going to be seeing that, for example, we have these two terms are equal. One is in plus and one is in minus. Okay, so one is g transpose x2. The other one is x2 transpose g. The m is just a constant. One is positive and one is negative. They just disappear. And in the end, you're left with these two terms. You cannot say any more, you cannot do any more simplifications after that. But from here, what we're going to be doing is that we're going to be defining this B, okay, matrix. It's a 3 by 3 matrix that looks like this. It just includes this part, So instead of, now this is just a constant multiplied by x2. We're going to make it into a matrix by taking this constant and multiplying by the identity. Okay, so this is exactly what you see here. So this is the constant multiplied by identity, which you have, just takes a number and makes it into a 3 by 3 matrix. And in the end, we write it in this form. Okay? Just a little bit manipulation. And we have the V transpose F con. Okay. If you started with some energy, energy, the rate of change of energy is equal to power. The rate of change of energy is equal to power. So from a definition. So if this is mechanical energy, what is this? What is H dot? Mechanical power. Right? And mechanical power is equal to something plus something. All of these are scalars, which means that they should also have the units of mechanical power, right? Everything, should be in terms of power. So this term should be related to power, and also this term should, have a units of power. The way what these represent is that the first term is equal to the power that's dissipated in the damper. Okay? And the second term, simply any external power you're going to be supplying by a controller. Okay? And in both cases, you see we have some sort of, there is some force multiplied by velocity. X2 also is the velocity. X2 here was the velocity. Don't forget that. So X2 is a velocity, which means that minus B X2 is also like a damping force. Okay? So this is the damping force multiplied by velocity. This is velocity multiplied by F1. And by multiply here, I mean the inner product, okay? Because these are just vectors. So from an analysis point of view, the rate of change of the total energy in the system is simply either it changes based on the dissipation, or if you supply external power, just it will increase. And you see that the power dissipated, so this B is always positive definite. So it's always positive semi-definite. And this term, it can either be positive. It's indefinite. We don't know what will happen from the outside. I can either connect it to. I don't know what I'm going to be connecting it to. What the controller will be doing from a power perspective. So this can be anything. However, with respect to this term, the first one, you see that we can always say that this is always positive. So x2 transpose multiplied by this matrix that's always positive semi-definite multiplied by x2 is always greater than or equal 0. This is just the definition of what a positive semi-definite matrix is. And there's a minus sign, which means that it's always going to be decreasing. Okay? If you have power in a damper, it's always going to be dissipated. So it makes sense. If you have power and friction is always going to be dissipating power. It's always going to be dissipating energy, which means that this H dot is less than or equal this product. This is very important. If you already know about passivity, this makes sense. If not, we say that this system, this mass damper system, we say that it is passive with respect to the input-output pair, F con and V. Okay? So this is something called passivity, and it's very important for control and also for analysis of system. Yes?
If there is no input, then it's same like a Lyapunov.
If there is no input, absolutely, yeah. We can think of this as some Lyapunov function. And in the end, you've shown that H dot is less than or equal 0, which means it's negative semi-definite, and you cannot say further. You can only conclude that the system is stable. You cannot say anything about asymptotic stability. You need to take a step further, analyze the system further, use something called Barbalat's lemma if you have time dependence, or Lassalle's theorem, for example, and so on. You just need more analysis. And in the end, you can really show that, yes, we will, so the H will go to 0 or some minimum, H dot will tend to 0, and the velocity will tend to 0, and the position will also tend, to something. It's not going to be 0, it's going to fall, the ball, if you simulate this ball, is going to fall, it will stop, but it will not, go back to the origin. There's nothing that's pulling it. That's exactly what the equation says. It's going to stop, but somewhere, So again, just as in terms of passivity, if you haven't heard about it, so this is just a recap on the side, that what passivity is simply, it's a concept in dynamical systems and in control theory in general. You say that a system is passive. The intuition is that a system is passive if it doesn't generate any energy. Okay? It's not generating energy by its own. It's either storing it or dissipating it. If you have a system that has some input U and some output Y, you say that the system is passive if you can find a non-negative storage function, so some function that's always greater than or equal 0, such that for all time you have this integral equation. And if you add some extra condition that the V, for example, is differentiable, you can rewrite it into this differential form, that V dot is less than or equal the inner product between U and Y. If you compare this definition to what we have here, we do have this, this passivity property for the system. Later on, we're going to be seeing why is this passivity property important. We have it. It's not clear why do we need to have passive. Or why do we need to be passive with respect to this input-output port. But later on, inshallah, it's going to be clear. Yes. Yes. So you see, H dot is equal, as an equality, it's equal to two terms. One of them is this one, and the other one is minus this term. So if you look at this term, it's always going to be positive or 0, okay? Depending on x2. It's clear? So because if you go back to the definition of B is just a diagonal matrix with positive numbers on the diagonal, okay? Which means that it's positive definite. It's positive semi-definite in terms of x1 and x2. So in the end, I have here that this is always positive with a minus sign outside. It means it's always negative. So H dot will always, if this is 0, H dot will always be decaying. Okay? If you simulate the system in any condition, you're going to always, and you plot, for example, H dot, you're going to be always seeing H dot, going to 0. Okay? Monotonically. So it's not like, it's going to be going to 0 and then at some point it's going to be going up and then it's going to go down. No, H will always going to be monotonically to 0, and H dot, is always going to 0, okay? Because it's always negative. Okay, let me rephrase this to be precise. So if you plot H, you're going to always find that H is monotonically increasing. If you plot H dot, you always find it negative. So the rate of change, how H will change with time, is always negative, which means that it's always decreasing. So H is always decreasing, while H dot is always negative. Okay, that to be precise. Any more questions? Okay. Yes, exactly. So this less than this inequality is just because of the blue term. Okay. And this one, it can be positive, it can be negative. We don't know. We don't know what the other side is. You know what? So this is the controller. So after you say, for example, what F control is, we can make a decision what the closed loop system, how it will behave. But for now, it's it's passive. Okay. So since you brought it up, I think I have to say it now. What if, that V and so F controller, right, is calculated by some dynamics. It has dynamics of its own, which means that I think let me see if I have this slide here. No, don't have it. So if F controller and okay, wait, okay, I'll stop. I'll not say it now, just because I think I have there belongs to a future slide. So let's keep it now. This is the standard way of dealing with the system. Let's try to do exactly the same with just written in a Port-Hamiltonian fashion. You're going to be seeing first of all, you already saw that from the beginning. We already started in the previous part that we were talking about energy, right? Passivity is naturally within a passive, within something that deals with energy. Okay? And we have an input and an output that are that you multiply together, and they should be equal to some energy dot and so on. So everything it makes sense. In the Port-Hamiltonian, this is completely natural. It's not like we're doing extra work. It's from the beginning. It's inherent in this, and you're going to be seeing how right now. So when we're dealing with Port-Hamiltonian systems, and trying to represent mechanical systems, usually you're going to be choosing the position of the point mass and the momentum, not the velocity, but the momentum, which is just mv. You can rewrite the energy, which is the total kinetic plus the potential in terms of p and psi, and the gradients would be equal to the following. Okay, just simple calculations. These gradients, they have a meaning. mg, what does it represent? The force due to gravity. Okay, it's just missing a minus sign, right? It's not exactly, no, it's just, but it's related to it. What about p over m? The velocity, right? So they do have a physical meaning. Usually these gradients, they're called a co-state variable. So the state variables are the x. So these are the energy variables, while the gradient of h with respect to x, we call them usually the co-state variables. Okay, so we have a state and a co-state. The dynamics, okay, that we just discussed a bit a while ago, can be rewritten into these two forms. Okay, in terms of this gradients. So you see clearly psi dot is equal to the gradient of h with respect to p, because it's equal to p over m, or the velocity, while p dot is equal to, this term was equivalent to the minus mg. So the minus mg is equivalent to minus the gradient of h with respect to psi. This term was equal to b multiplied by the norm of v multiplied by v. We can rewrite it in terms of, instead of the norm of v, into the norm of p over m. And the v itself can be h, partial h by partial p, okay? Which is the gradient of h with respect to p. The control part is the same. And the output velocity that corresponds to this f, the control force, is simply partial h by partial p. We just have this as an output, extra output equation. If it's clear to you, you can always rewrite it, into this form, just add, zeros here and there just to make it into a matrix form. And you clearly see this is the Port-Hamiltonian frame, okay? The Port-Hamiltonian representation of the mass damper system. Any question? Yes.
Usually when we start here, we start with the regular Newton equation, right?
Yes, the Lagrangian form.
Right, Lagrangian, which the b, the psi dot equal v.
So this one, the down, is usually the standard Lagrangian form, where m psi double dot is equal to something.
Well, I mean every time with the Port-Hamiltonian, because when solving the mass spring or mass spring damper, the Hamiltonian function is the same, because the R matrix only appears in
Absolutely.
the second one.
Yes.
So Hamiltonian is like the total energy anyway.
Absolutely.
So R doesn't appear in it.
Absolutely. Exactly. It's the stored energy. H is the total energy stored in the system. Damping is something else. Okay?
Sorry.
Yes.
Just building on this question. So we must always have a base equation that we're trying to rearrange the Hamilton, using the co-state variables.
Yeah.
We're trying to rearrange the base equation into something that's represented in the Hamiltonian framework.
This is one way of doing it, not the best one, but it's one way of doing it. Okay? But the Port-Hamiltonian, so this is only, just to save 3-4 lectures. And okay, I'll try to be more, politically correct. So this is one way of writing a Port-Hamiltonian equation. A lot of people even do that, in the literature. They just start with the equation. I already molded. Why start from scratch? And then, I just rewrite the equation. Say, okay, this is this term, and this is that term. These are two are skew symmetric. This is, act like damping, and you just hand engineer it into a Port-Hamiltonian way. There's another way, okay, that's more formal, more systematic. Just like how you can use variational principles and you can derive in the Lagrangian framework the equations, with Euler-Lagrange equations, you can do exactly the same in the Hamiltonian side. And there are actually something called Hamilton's equations, and this is very popular in the geometric mechanics literature. Okay, so this comes naturally. Okay, And you can always go from the one to the other, provided that the energy has some sort of, some properties. For example, the quantum mechanics people, they always like to work in Hamiltonian. The gravitational guys and theoretical physics, in the gravity and in relativity, they work in the Lagrange. Okay, one of the reasons why some people claim that one of the reasons why we're not able to do quantum gravity is because that the Lagrangian picture and the Hamiltonian picture, sometimes they don't match. For our case, for mechanical systems, we're down on Earth. Everything, can always ride both. But from a philosophical point of view, that when we want to do later on control, okay, they do make a difference. You start to apart, because the equations you start differently, and the way of thinking is different. And this is exactly what you're going to be seeing right now. We're going to be trying to do the analysis with this system. You should expect we get exactly the same what we got, the result, right? This orange part is the J. You see it's clearly skew symmetric. The B part is this something, it's positive definite. It doesn't have any minus inside. We just have the minus outside. So this is positive semi-definite matrix. And we have the G, just as an input, that is just the G transpose. And if you try to do the energy analysis, we start with the Hamiltonian, which is the kinetic plus the potential energy. H dot in this case is simply, we're going to be writing it, in a compact form. So the partial H by partial X in general, transpose will multiply by X dot. You can write X dot, using the Port-Hamiltonian equation. You can plug it in. You see you're going to have one term with the J, one term with the R and the minus, and one term with the G and the F com. Yeah. What happens to this first term? It's equal to 0, just because of the skew symmetric property. It's always the case. Even if it's this term, even if this J was a function of X. Which means that if you have a nonlinear system that's very nasty, and you spend a few minutes or maybe a few hours trying to just cancel one from this side, this term with that term, this term with that term, and so on. If you really deal with something complicated, in the end, it's just inside of the J. If you write it in the Port-Hamiltonian framework, so this is a technical advantage. When you're doing analysis, everything in the J just disappears. But it's not for it's not just some magic. It's not because we wrote the equations in a fancy way. It's inherent to what the J is. The J represents the interconnection structure, how the different subsystems are interconnected to each other. So it doesn't matter whether you have, for example, a mass and a spring and a damper connected in series or in parallel. It doesn't matter. In the end, the J, it will look differently, but it doesn't affect the energy. The energy stored, doesn't care whether you have, for example, if you have a resistor and a capacitor and an inductor, whether in series or parallel, or two in them in series, one in parallel, or I think all of these are just topology, how you connect the different parts together. The energy balance should be in the end that energy stored should be dissipated or, either stored. If you have a mass spring damper or an RLC circuit. So all of this, the J term just disappears. It's equal to 0. We're left with these two terms. You just plug in what the R was and what the G was, and then you can rewrite it in this form. You just take a few minutes to write it yourself. You're going to find that it's equivalent to that. Immediately, it's just one liner. You might say, okay, but there it was, just 3 lines, and now I just reduced 1 line. Of course, but if the other one was, 10 lines of trying to do analysis, it's still 1 line here. Okay, because of this, of the skew symmetry of the J. You don't even need to do math. You can even just look at the system. And this is again the power of the Port-Hamiltonian, because the J part, anything in the J part, the skew symmetry will always disappear from the energy balance. Anything in the R will always appear like this. That there's a minus and there's the Hamiltonian, okay, the gradient of the Hamiltonian or the co-state transpose multiplied by this R and co-state. And this is always positive, and this means this term is always negative less than or 0. While the G, it always appear like this, and you always, can flip it and rewrite it like V transpose F, which is the power supplied from outside. No matter how complicated the system was, even if J, R, and G were functions of X, you will exactly get the same result. This is very powerful, okay, to deal with nonlinear systems in this way. Yes.
So, in this case scenario, for example, I think there's an emphasis on the fact that we're dealing with a mechanical system.
Yes.
But what if we have a system that's not quote-unquote mechanical in nature?
What if it's not here? So what if it's your research? So you research it on your own. It still works, okay? You can always, you can include, if you remember what we said from the beginning. We said from the beginning that the Port-Hamiltonian or even port-based modeling, it can deal with different physical domains. Okay, you can have even one system that has, you know, an electrical part and a magnetic part and a thermal part and a chemical part. You can have some very complicated stuff. Okay, for example, you can rewrite in this equation one of the most difficult equations. For example, for a nuclear reactor, you can have thermomagnetohydrodynamics, thermal part and magnetic part, Maxwell equations with hydrodynamics, with Navier-Stokes, and then you have all of them in a PDEs even. You can rewrite it like this. Okay. If you're interested, yes, you can do a lot of stuff, but it's the same equations. Okay? Of course, it looks the same. You know, the J is there, the R is there, but if you work with PDEs, okay, you're not going to be working with numbers, you're not going to be working with vectors, and you don't have that transpose and all of these nice stuff that, you know, just child's play. Even when we go to the fully actuated, you know, hexarotor, the flying end effector, we don't even have this, you know, transpose. We don't have this RN structure. And this is why it's a little bit complicated. But if you have the tools, if you have the right tools, for example, the guys that took for example, the geometric control course, they were exposed to these tools. You can still rewrite it, you know, can use these tools to rewrite the system in the Port-Hamiltonian fashion. This is exactly what we're going to be seeing now. So the standard equation of motion, H dot is equal to H multiplied by this, you know, matrix representation of the twist, and we have the conservation of momentum. Okay? Standard equation you should be familiar with. Now there is no energy, but the energy is there. We still have a mechanical system. It's kinetic plus potential energy, and I can always rewrite. So it's easy to immediately to see that the gradient of kinetic energy with respect to momentum is equal to, in this case, so in the previous example, the gradient of kinetic energy with respect to momentum, what was it? It was velocity. So here, the gradient of the total kinetic energy with respect to the generalized momentum, what it would be? The twist, which is the generalized velocity. This is no, you know, it's not a coincidence. It's always the case. Okay? Actually, because the momentum is defined as, from the definition of the momentum, is defined as the gradient of kinetic energy with respect to the twist. This is how we define momentum of any system. For example, if you work with manipulators, for example, you know that we have Q dot, you know, to be the velocities there, generalized velocity, and the M of Q, right, is the mass matrix. It corresponds here, for example, to the inertia of this body. And there, how would you write the kinetic energy? You would write it half Q dot transpose multiplied by M of Q dot. You can define something called the generalized momentum for the manipulator, and it's equivalent to M of Q multiplied by Q dot. You know, so if some people call, for example, pi. If I take the kinetic energy again as a gradient with respect to pi, I go back to Q dot. So pi. So we call this, you know, there's some duality. Momentum and velocity are always dual to one another because through this inertia matrix. This is no coincidence, always the case. So whenever you have any mechanical system, you can always go back between momentum and velocity, generalized velocity in general, using some inertia. Okay. So this is the first equation. Okay. This chi variable is simply something that takes care of the geometric structure of, okay, dealing with homogeneous transformation. Okay, I'm not going to go into details. Okay, you need to take a whole course on it. These guys already took it. So I already see, for example, only 2 that did not take the course. So just for now, think of them as, you know, extra complication, just because of the fact that we're dealing, you know, with this, you know, geometric stuff. But in the end, if you have the tools, there will be just some map chi h, and the chi h star will be just the dual of this map that goes, you know, in the opposite direction. We're going to be using the first map here to represent this equation that corresponds to the kinematics. And the second one, what does this look like? So this orange term, what does it remind you of in the previous example? No?
Dissipation?
The orange one. The gradient of potential energy. You all know, right, that gravity can be represented like potential energy. And what is the force due to gravity? Is equal to minus the gradient of this potential energy with respect to position. Makes sense? If I have here something that's, you know, 3D, that's doing translation and rotation, the same concept holds. If you write the gravitational potential energy like this, it's a function of psi, and this psi was actually a part of the h, of the pose, hb with respect to I. Then if I take the gradient of this potential function with respect to the h, okay, and by h here I mean the hbi, which is the pose, and I do the minus sign, I should get something like, like a gravity wrench. Okay, it's not just 100%, matching, because I don't go from a twist to h dot directly. I have this map, so whenever I come back with a gradient to the wrench, I have the dual of this map. This is all, just the intuition behind why do we have these two maps. Okay, so in the end, this minus of this term corresponds simply to the gravity wrench. Okay, not a lot of people, think of the gravity like in this complicated way, because in the end, for example, if we're doing control, we just cancel it. But this is very helpful, to write the equation in the Port-Hamiltonian way, just like what we did in the previous part. What about the green one? Is it damping? Does it look like the damping term? It looks very much like the damping term, right? But it's not damping. This is, this answers the question, Muhammad. Can I start from this equation and you say, I can always, rewrite it in a way that I can put it into a Port-Hamiltonian way? You can sometimes do mistakes like this. You can think of this like a damping term, while actually it has nothing to do with damping. You're going to be seeing why in a bit. Okay? And then we have the last two parts, which is the wrench for the control and the wrench for the interaction. You can always rewrite it into this form. And you see now that the chi and the minus chi transpose, they come on the diagonal part, which means that they are skew symmetric. So even if so far you don't know what they are, right? You never work them out, very complicated stuff. But in the end, they're just skew symmetric. If you do any energy analysis, what happens to them? Just disappear. And also the same for this term, the j as a function of p. The j as a function of p, which corresponds to the gyroscopic terms and all of the Coriolis terms and all of these stuff. They are also inside of the j, not inside of the r. Which means that, and this j, you can really show that it's actually skew symmetric. Which means that all of this term, when I want to do energy analysis, for example, as follows. So I take the h dot, right, the total energy, kinetic plus potential, and I want to now do, what is h dot equal to? So I take the gradient and multiply it by x dot. And this is where you start to face, technical difficulties, because x dot does not live in Rn, okay? Because x itself does not live in Rn. So, things get a little bit, nasty, technically. Eventually, you can, rewrite it into, you need to have more machinery, more mathematics. This is related to differential geometry part. And you need to look at not the gradient of h as a vector, but you need to think of, the differential of h as a covector. And you take this covector and you pair it with the vector x dot in proper spaces. You need to define a duality product, things that are a little bit nasty. But in the end, I'm just going to be writing in this slides like this. I'm going to be keeping it, h partial h by partial x transpose multiplied by x dot. But keep in mind, this is not 100% precise. Okay, just there's still more technical difficulties that we need to challenge. We need to take into account. But even with these technical difficulties, when I plug in the x dot with the j and the g and so on, what happens to the j term? Everything with the j term, it's also zero. Even if it's nonlinear, even if I have different spaces, even if after all of these technical difficulties, it just disappears. You have zero, and you're left only with the first term. The partial h by partial x multiply, I can retranspose everything. This is just a scalar, so I can retranspose it. So if I had y transpose gx, I can rewrite it as x transpose g transpose y. Okay? And in the end, you're just left with these two terms after, you just plug in what the g is and what the partial h by partial x is. And they're simply two terms that are a pairing of some wrench and some twist, like some force and some velocity. The first one corresponds to power supplied by the controller, and the second one, because now we have some interaction, with the environment, with this flying end-effector, we have also power supplied by the environment in this symbol. Okay.
So like here, looking at the H dots, you mentioned of course, we can't just do it directly here. We need to take into consideration the structure of the system.
In the equality, but this is the same. So the first term, which is the rate of change of h, It's well defined. But what is equal to? It's not equal to the transpose of these two terms. That's right.
Here we're dealing with two different states.
Which ones?
In this case scenario, this x dot, quote unquote,
Yes.
deals with talking about the transformation matrix and also the generalized.
That's right. Yeah.
So if we're trying to use the differential geometry, for example, and we're looking for the pairing, so we have to do it in two stages, the first one or the second one. Is there like a way to combine both of them together, or we have to do it individually?
Individually for each state, you mean?
For each stage, yeah.
Yeah, but that's easier. That's actually easier. If you can decompose it, if I can take the equivalent of the gradient with respect to h dot first, and then the equivalent of a gradient with respect to the p dot, it's much easier. And in fact, you can do it. Because the state space itself was a combination of SE3 and R6 star. So I can, when I'm writing the h dot, and I'm going to have a tangent space in the SE3, and I have a tangent space of R6 star, which is R6 star, and then I can, decompose them, and I can do this one alone and this one alone. But in the end, it just disappears. Everything just disappears because it's skew symmetric. That's exactly the same. So this is the conclusion, that no matter how complicated this was, in the end it's equal to the rate of change of kinetic plus potential energy is the power supplied by the controller and power supplied by the environment. There is this graphical representation that this equation is just in this diagram there. Okay? And this is exactly what the bond graph does. The bond graph, or this graphical representation of Port-Hamiltonian systems, is nothing else than capturing this physical, equation, this power balance. What you see on the top here in the C element, it simply says that I have some storage of H function. The H function is a function of HBI and a function of PB. So I have a function of the two states. These are my two states. These are my energy variables. And as a flow variable, I have x dot, and as an effort variable, I have the gradient of H with respect to x. Okay. And then this was, this is the arrow. It means that this is storage of energy, and this is, this zero. It means I'm gonna flipping the energy. So energy in is equal to. So this is energy out, and this is energy out, but just with a minus sign. This is just a small technical detail, not important. But in the end, you see what this DRB is. It's something that takes power from the controller, power from the environment, and power that corresponds to H dot. Because the pairing of X dot and the gradient of H with respect to X is the H dot. The pairing between the wrench and the twist on this side is the power supplied by the controller. The pairing of the wrench and the twist on this side are the power supplied by the environment. So you see, we always have a pairing between two variables, the effort and the flow. Okay. This causality stroke, which is this bar at the end of the arrow, it simply says that where the effort is an input, and the effort is always the side that's not with the arrow. So here, for example, wrench is the effort. Here, the wrench is the effort, and in this side, the gradient of H with respect to X is the effort. Okay. You can rewrite, if you really want to see what this dr is, you need to take this equation that we had, rewrite it in a very peculiar manner to get this form. You just need to. There's nothing new. Just rewriting of the equations. I have some inputs and some outputs. Here I have one input and one output, one input and one output. And here, don't forget that the X itself was two states. So I have two states as an input, two states as an output. Sorry, two signals as an input, two signals as an output. And this is why you see all of these four outputs is equal to something multiplied by 4 inputs. Take a look at what's inside of this map. What is your observation about it? It's skew symmetric, exactly. It's completely skew symmetric. What does that mean? It means that if I pair this side with this side, I should get equal to 0. This is exactly what it means. So if you pair the first with the first, and then you add, the second with the second, and then you add, the third with the third, and then you add. By the way, what we're adding here are scalars, just numbers. Right? So pair the first with the first, you get a number. You add this number to the second and the second, the third and the third, the fourth and the fourth. In the end, you should equal to 0. If you look at this equation, we just calculate all of these numbers. The first two lines are the H dot. The third one is the power supply by the controller. The fourth one is the power supply by the environment. In the end, this is, so you have different ways of, looking at the system, okay? It's not easy, just to, in one, for the first time to get your head around it. You need to have, days of rewriting, systems that you're already used to into this form, but in general, it can be done, okay? So if you want more examples, so I leave this up to you. You come and say, okay, I have the system. I would like to write in the Port-Hamiltonian form. Can you help me? And I'll try it. Okay, so this is just, practice makes perfect. You need to do this again and again and again until it becomes just a habit. After some time, you start to see everything in Port-Hamiltonian, just like Neo in the Matrix, you start to see everything, with zeros and ones, okay?
Oh, sorry, sir.
Yes.
Question.
Yeah.
So is it always the case now? You mentioned something about we have the output, we have the skew symmetric matrix in the middle, and we have these as inputs, or however it is you want to look at it.
Yeah.
So it's always the case that whenever we have a relationship between the output and the input being a skew symmetric matrix, and then we add both of them together, we'll get zero. We'll multiply both of
You're
them.
talking about this big skew symmetric part, or you're talking about the skew symmetric one, which is the J alone, because when we were talking in this form, which is the x dot equal to J of x multiplied by the gradient of h with respect to x, this was the J part, which was skew symmetric.
Yeah.
And then we had here the G and the G transpose.
Yeah.
What we just did here is that we took all of these and rewrote them into a J, and we took two, these are the G's with the minus, and these are the G transposes, just double them to write it into this form. Okay? It's exactly the same.
I mean, I'm talking about in the case of we're talking about the big.
The big one is always skew symmetric. If you rewrite it like this.
Right to this way.
Yes.
And whenever we multiply the variables here and the variable at the other side, it will always give us zero.
Because of the skew symmetry, yes. The sum is equal to zero. The sum is equal to zero, yes. What I just said is exactly what this graph says. Because this Dirac structure, so this is what's called the Dirac structure. The Dirac structure is simply something that, it maps inputs to outputs. So here, all of these ports, some of them are inputs, some of them are outputs. As I said, so wrench is an input here, wrench is an input there. Here, the partial h by partial x1 is one input, and partial h by partial x2, which is this term, is the input. And then we have as an output, you have the minus x dot, x1 dot, and x2 dot. These are the two inputs. So, so this is exactly what this Dirac structure does. It just takes all of these 8 variables, 2 here, and 4 here. So all of these 8 variables, and they ties them together into some skew symmetric form. What all of this, all of this math corresponds to one thing. It says that rate of change of the energy that goes into this port is equal to power supply from here, power supply from here. This is exactly what the math says. So if you're working with bond graphs, I don't even need to write a single equation. I can always, I can think of the system exactly like this. It's just, all of the equations, they're already there. And this is very important. You can even have this in a computer code. You can even have a program. For example, there's a famous program called 20sim. Okay? And they try to have, that you can actually build the system. Instead of writing a mass spring damper just, as an equation, as a second order differential equation, you can just draw it like this, and you just run simulation, and then it simulates stuff for you. Try to do these figures as an assignment. Try to do it for the mass and spring and damper, and for the mass and damper, and for the mass, and see what changes. Okay, so that you really see what the D is, what the C is, and so on and so on. Yes.
Closed loop system at the end.
There's no, okay. Here, I added, this circle that says impedance control. Because what we're going to be doing in the next part is that we're going to be thinking of the controller as another subsystem that's written in Port-Hamiltonian connected to this one. So yes, we can do that. Exactly. So what you see here is indeed the closed loop system. Yes, you're right. If we remove the controller part, I have a system that has 2 parts, 2 ports to be connected. One to the environment, one to the controller. Yes, you're absolutely right. Yes. For the Dirac structure, yes. This one here is J. This one is G transpose, G transpose. This is minus G minus G. It's indeed. Absolutely. No. The R actually should be outside. This is why I removed it from here. The R will be an extra information. It's not in the Dirac structure because remember, the Dirac structure is symmetric, right? So it's just energy flow. I don't have, dissipation there. Just like here, for example, where is the Hamiltonian? So this is a very good question. So first of all, where is the R here? The original system did not have an R. This is why you don't see it inside of the Dirac structure. But this system has energy storage, right? Where is it inside of the Dirac structure? No, I'm talking about the H, the storage of energy. So it doesn't appear in? No, I'm talking about this H of X, which is the half. If you go back to the previous slide, it was let's go back. So this H, kinetic energy plus potential energy. Why didn't it appear in the Dirac structure? Go back to the Dirac structure. Where is it? It's not there. If you did it the same with something with the damping, also it will not appear in the Dirac structure. What does this tell you? Absolutely, exactly. Because the Dirac structure, it only highlights the interconnection structure, that you have two ports and something with kinetic energy and something with potential energy and so on, and the states and everything inside is just it just disappears. It doesn't appear at all in the energy bands. However, the damping itself, the damping part, is something extra. If we had here damping, we would represent it like an extra element. Usually we call it with an R element, like a resistive part. And the C here corresponds to like a capacitor part. This was the idea that Henry Painter had when he was talking about bond graphs. He used the C element to correspond to I have some sort of like something like a capacitor. It stores energy, and the R part is something like a resistor. It dissipates energy. But these concepts, they are general. In mechanical systems, the dissipator is the friction, for example. In electromagnetism, the dissipation, for example, is the electrical resistance. Or you can have, like leakage and stuff like this in magnetic circuits, but more on that. Yes.
We're talking about the damping and R, but you said the system doesn't have an R.
Yes. We're talking about the fly end-effector here. It's just a body that flies in the air if you apply some wrench to it.
So
there's no damping.
So previously, when you were explaining the course, I remember the term of 6D damper and 6D spring.
Was this related to the control part or the original UAV? So does a UAV have some damping or some stiffness? It's just a rigid body. You throw it in the air, it falls down. It rotates, it just rotates and then falls down.
It doesn't have any damping.
Exactly. I'm sure talking about a rigid body, Take the drone, hold it in your hand, throw it in the air. It just, flips and falls down. What's the equation it follows? It follows this equation. Don't give it any control. Don't give it any, external forces or interaction forces. It just, follows this equation here. And H dot is equal to 0, It just falls down and dissipates kinetic to, it transfers kinetic to potential and just, hits the follower and that's it.
Yeah. So the case we have, for example, would it still be the case that when we multiply this, we take the sum of the inner product of these different variables, like we still get 0 even without the R?
Yes, you will be. So I'll tell you exactly how you would, for example, add a damper here very easily. Assume that this power supply by the environment is not power supplied by the environment, is equal to power supplied by a damper. Okay, so I have a wrench that corresponds to the damping, and I have a twist that comes outside. Let's say that I take this twist and I multiply by some damping matrix, some 6x6 matrix. What do you get? You get a damping force, damping wrench. Take this damping wrench and say it's equal to this interaction. So you just, I just close this loop with something, just takes the twist as an output, multiplies by 6x6 matrix, and I say it goes back as the wrench. If you do that, what happens here? You see what first of all, it has to be with a minus sign. Okay, so the wrench is equal to minus KD multiplied by the twist. If you substitute this part, here, let me try to see if I can write it down. So if you substitute this part like this, if let's say that interaction wrench, let me see. So interaction wrench is equal to, okay, it doesn't work. Okay, 1 second. Let's try to do something. Okay. So let's say that you assume that the interaction wrench is not really for interaction, but it's simply a damping wrench. Okay. And it's equal to minus KD multiplied by the twist. Okay. And then if you go back to the original equation that we had, my claim is that nothing will change, okay, except for the following, that H dot, okay, so this was the total energy, which was equal to the controller paired with the twist, plus the interaction, which is now the damping part, paired with the twist again. I can rewrite this. The first term doesn't change. The second one, I can rewrite it like this. If you just plug in this term here. So what you're going to have is something that looks like that. Of course, this will be a minus sign multiplied by the twist. What do you say about this term? If you choose KD to be always, greater than or equal to 0, what happens with this term? It's always positive because it's damping. What does it correspond to? Power dissipated due to damping, exactly. And in the end, we have this is less than or equal the wrench, the pairing between the wrench and the twist. Which means that, what does this mean? What does this mean? System is passive. If you go back to, so this is just the math. But if you go to the term passivity, if you just go to the intuition behind passivity, what does passivity mean? Passivity means a system can either store or dissipate energy, but not generate. Now take this exact same concept and take a look at this figure here. So this figure, it has a C element, which means it's for storage. What the extra stuff I did right now is just an R element that corresponds to dissipation. And it has here some impedance controller. I haven't talked about the controller yet. But so far, we've made this part passive. Is this system stable? If I remove the impedance controller and I remove this port, is it stable? Passivity implies stability. So if you have a system that's passive, this means that it is already stable, because I already found the Lyapunov-like function that it will start to dissipate. It will start to go to 0 as the system evolves, which is exactly what the stability is. Do I have asymptotic stability? No. It depends on the properties of that. You can add extra conditions on this energy function, and then in the end you can make it into really asymptotic state. Okay? But at least passivity is enough for stability. Now this is a very important part. Assume what I just did now for the interaction port was actually for the control port. So now let's just flip it. I should have done it this way in the beginning. So I should have chosen actually that the control part and the twist are related by a damper, and this one is the one left open. So if I get this equation, so for example, the power supply by the controller in the end will be power dissipated, so it will always be less than or equal to 0. And in the end, I'm going to get H dot is equal to this power supply by the environment. Do you know what the model of the environment is? Of course not. You don't know what you're going to be dealing with, what you're going to be interacting with. Can you make an assumption? Some people fall into this pitfall. They usually say, just like what we did now, I'm going to assume that the relation between the wrench and the twist is like a spring or a damper. And then I'm going to do a Lyapunov analysis, and then I show that, yes, my controller is stable. This is completely wrong. Because what if the system is not a spring and a damper? What's non-linear spring and non-linear damper and so on? And this is why passivity is very important. If you can show that everything on this side is passive with respect to this port, this means that if the environment is also passive, so in other words, if I interact with this controller and my original system with this passive environment, I have guaranteed contact stability. This is a new term. Contact stability is not stability, just for the system that's not interacting. Contact stability, it means I have something interacting with the environment. It's maybe this drone will be me pushing on a wall, opening a valve, writing something. So it's interacting with the environment, but I don't know what the environment is. I'm only going to make one assumption. What this assumption is, the environment is passive, which means that the power supplied by it will always be decreasing because it cannot generate power. So this is the only assumption that I'm going to be making. And because the power supplied by the controller itself is also passive, I have guaranteed contact stability in the end. So starting from this point, what is the main goal we need to do now to make sure that we have a system that can interact with the environment in a stable manner?
If you
Design
when you
such that it is passive. Call it whatever you call it, call it an impedance controller, call it whatever, just call it. I need to design a controller. So if you want to design a controller for interaction, I need to make sure if it is passive, so that or at least, and this is the trick, even if the closed loop system is not, even if the impedance controller itself is not passive, I only need to make sure that the controller and the system I have are both passive, such that the closed loop system is passive, and in the end, I have guaranteed stability with respect to the open port of the environment. Is this part clear for everyone? Yes.
Guarantee for sure that the environment I'm going to interact with is passive.
Absolutely.
How can I ensure that stable contact, knowing that the environment, I'm not sure if it's...
You cannot. That's the thing. Everything we just did now with Lyapunov analysis, this idea that I have some energy-like function and it starts to dissipate and it goes to zero. But what if something is pumping energy? What if I have something that's continuously adding energy to the system? And this is why passivity-based control is not enough to really work in real life. And this is the topic of next lecture, inshallah, when we talk about energy awareness, not passivity-based control, but more like energy-aware control. Okay, so this is the new paradigm that we're going to be talking about next time. So it's a newer paradigm. It's like, so impedance control compared to motion control is one extra stuff. So actually that's the next part. So let me, who does not know about impedance control, I said it a lot, but who doesn't really know about it? Okay, you know about impedance control? Watch the lecture, perfect. Okay, so I'm just gonna repeat this part, from the lecture, just to refresh. Impedance control is one type of interaction control. Okay, compared to motion control, it's a different paradigm. It's a different way of thinking. The first one is that we want a robot. For robots as mechanical systems that are interacting with the environment, this is the starting point if we want to do control of any robotic system. Because a robot, we don't design a robot to move from point A to point B and to reject disturbance. We design a robot. Actually, the word robot means working slave. So the slave should work and should interact with the environment. So it's already in the definition of it. You cannot have a robot that just goes from point A to point B. This is just it's in general. How much time do we have? What's time now? 1:15? 11:15. Okay. So I'll just try to finish, inshallah, in 15 minutes. So interaction control means that you want to interact with an unknown environment in a stable and safe manner. It means that on the other side, I have an open dynamical system. I don't know what the environment is. And it means that it should look at bilateral systems. And this is very important why we had, this port. We had a wrench and a twist that will be connected to something outside. So you're not controlling the force alone and the position and the pose alone, or the wrench and the twist alone. You're controlling a behavior between both, a relation between both. And this is the idea of impedance control. So impedance control was introduced by Neville Hogan. Okay, I think it was in the late 1985. He published 3 papers. They're seminal, so they're very popular. And actually these numbers, these citations were from last year, so they will be higher now. The idea is very simple. The idea is that if you look from the port, by the way, just as a side, if you go to these papers, I'm going to put them for if you're interested, you're going to be finding that Neville Hogan was using in these papers bond graphs. So he came up with this idea thinking in terms of ports, thinking in terms of bonds. There was no Port-Hamiltonian system theory at that time. It was not formulated yet, but he was working, with just the standard bond graphs. The whole idea is simply that if you look from the open port between the wrench and the twist, just make the environment see the closed loop system as a mechanical impedance. What does the word impedance mean? The word impedance, it simply means, it comes from the electrical side, from the electrical domain, but from the mechanical domain, it means there's some equivalent inertia, some equivalent stiffness, and some equivalent damping. What does the inertia do from a Port-Hamiltonian perspective? What does the inertia do? It stores what? Kinetic energy. What does the stiffness do? Stores potential energy. What does the damping do? Dissipates energy. So if you have the closed loop system is a mass and spring damper, it doesn't have to be linear. Don't think of the linear spring, that just goes back and forth. It can be a nonlinear spring. It can be a nonlinear damper. It can be a nonlinear inertia. So no assumption on linearity. Even a lot of people, just fix with the linear because of the tools that they're able to do analysis. But in general, you can have nonlinear stuff. But if the open port sees the controller and the system, which is the closed loop system overall, if it sees it as an equivalent mass spring damper system, you have guaranteed stability whenever this environment is something passive. So this is the main idea of Neville Hogan. And there's something that has the opposite. There's something called an admittance control. The admittance control is simply, instead of impedance in, instead of force in, velocity out, you have the opposite. You have velocity in and force out. Okay, in terms of the bond graph, it's just instead of the causality stroke being on this side, it becomes on that side. This is the only difference. Now, very quickly, what does an impedance controller look like for the mass damper system? These were the original equations of motion. And then we have the impedance control law that simply would cancel the gravity and add the stiffness and add a damping. So cancel gravity, add the stiffness force, and add the damping. If you plug in this equation into the original one, okay, you get something like this. The gravity just cancels out. And of course, there's a very big assumption here that we know what the gravitational constant is, and we also know what the mass is. This, it depends on a model. But afterwards, you get this equation, which we can rewrite into this form. What does this look like? Just a mass spring damper system. Is it a linear damper? No. It's B of V, it's a function of the velocity. It changes as the velocity changes. But in the end, it's linearly multiplied by the psi dot, which is the V. So I have an equation in terms of psi dot, psi double dot, psi dot, and psi, and equal to F int. What does this remind you of? Simply just a mass spring damper equation. So looking from these two, from this side, from the port, how is the closed loop dynamics behaving? Just as a mass and spring and damper system. That's it. Can we take this same concept and apply to the drone with all of just the extra technical difficulties that we're working, with twists and wrench? It works exactly the same. So if this was the system that we had for the drone, we had the Port-Hamiltonian dynamics, and I have this impedance controller. What I just need to do are 3 things: cancel gravity, add a spring, and add a damper. That's it. The damper is the easiest because it's just, just some matrix, the KD multiplied by the twist I just showed you with a minus sign. The spring is a little bit difficult because whenever the first thing when you talk about spring is that you say, I have delta X, and then multiply it by a stiffness matrix. But this delta X is only if you have a translational part. What if you have a rotational part? What about the rotational part? So some people say that I'm going to be using Euler angles, so desired Euler angles, desired actual Euler angles, and then I have a linear spring. So I just have, these two springs. This doesn't generalize well, has very bad properties. And when you use it for interaction, you get horrible stuff. Okay? And this is one of the very big, results in force control in general, that people that started to use, just linear springs like this, they got very bad results, very weird results. That should not be the case. And actually, they prove that you get better results when you do everything geometrically consistent. Okay, so I'll give you some reading material if you want on that part. But in the end, the virtual spring looks something like this. Forget about the details. It's just a wrench due to spring, wrench due to damping, and I cancel exactly the gravity that I had. So in the end, what you see there was everything in this side here is a Port-Hamiltonian system for the controller itself. So the controller itself is now a Port-Hamiltonian system that has a C element, corresponds to the virtual spring. So I have a virtual spring now between the tip of the robot and the desired frame I want to be in. I have a damping term, okay, a virtual damper that's just dissipating the energy. And I'm canceling the gravity. I'm just compensating for the gravity. I just need to cancel it out so that the drone can fly. So the gravity, you remember the original system had some positive, gravitational potential energy. So the Port-Hamiltonian system of the controller would have negative gravitational potential energy. And in the end, you just cancel these two out when you're doing analysis. So this is this C element. This C element is for the spring, and this R element is for the damper. Of course, we have now a different, Dirac structure that corresponds to how these ports are connected to each other. Okay, so a little bit more details, but you're going to be seeing the exact same behavior. And now I'm just going to show you some results. Now take this drone with this controller, right? And take the end side of the spring, which is the desired place, put it behind the wall, and just pull further. Just take this desired frame and put it back behind the wall. Go back and back and back. What do? You just keep on pressing more and more on the wall. This is exactly what you see here. So there's a force sensor behind the this wall or this plate, and the drone is pushing on this force sensor. And what you see here in the top figure is the forces. What you don't see is that the desired frame is going back and further. You're just pulling harder. This. So the drone wants to push, okay, and it wants to go to this desired frame because of the spring force or the spring wrench, but it's not because of the wall. And this means it's pushing further on the wall. This is exactly the behavior. What I want to point out here, I don't know if you saw it or not, or if you caught your attention, but I'm going to replay this and try to catch what's going on in this figure, the lower plot. One of the motors, when we start to push harder and harder, one of the motors start to go into its lower limit. So we're reaching actuator saturation. You see what's happening to this propeller? It's stopping. Why is that? Because I wanted to push further, okay? And this means that the control allocation part is asking this motor to produce negative thrust. The propeller itself cannot produce negative thrust, so we just, say, okay, negative thrust is 0. We just make it into 0. Something like this, thresholding a controller or a control output usually is a source of instability in classical, if you're doing classical control. Do you see any form of stability here? It's completely natural, right? Imagine you're pushing with your hand. You keep on pushing and pushing and pushing until you reach the end. What happens to you? You just get tired and you just go back. If you're pushing so hard, you don't fall down. Like you're not unstable as a whole. This is exactly the same behavior. Of course, you're saying, okay, it's very natural. It's very natural until you see, the other case that it's really, something that it doesn't work. And I'm going to show you in a bit an example that doesn't work. Yes.
It's like what is like the replication part of the system?
No, no. It's an extra source of uncertainty. We call it a parametric uncertainty, that I'm asking the drone to produce this range and it's not producing it. So if you do the energy analysis, if you do the Lyapunov analysis, you're going to find there's an extra error that's not, it's not removed. Okay. Now what I'm going to show you something extra is that what if we want the range I'm pushing with to be regulated, which means I want to do in the same time pose control and also range control. Okay, so in the previous example with a standard impedance control, you cannot tell the drone or any robot push with this force, push with 1 Newton or 2 Newton or 3 Newton. You cannot regulate the force. In this controller, you can simply you can do what's known as variable impedance control. Variable impedance control is very simply just changing the stiffness of the spring. That's it. Of course, because here we're working with a 6D spring, okay, the details will be a little bit more complicated, and you need to make sure that you are stable. The main problem is that once we do this approach, we're going to be losing the passivity. We're not going to be passive anymore. Okay. And you're going to be seeing here that, of course, there are more details. Okay, I'm going to skip them just for time. And I want to show you this video where you see here the force we're pressing with is actually being regulated. Okay. So there's always a step behavior. That means that we're telling it to push with initially 1 Newton and then 3 and then 5 and then 7 and then 9 and so on. Okay. So it's pushing, by a desired force that we want. Okay. Same behavior, but it's just, pushing. And to really show you that we can do both the position control and also the pose control, in this video, you see that the drone is pushing with a constant force of like 5 Newtons or something. And at the same time, we're telling it, just to rotate. Okay. This is the full actuation. This, of course, just because of the full actuation. A normal drone cannot do that. A normal under-actuated one cannot do that. Okay. So it's pushing, and at the same time, we're telling it, just tilt a little bit. There's no exact control of the tilting, and this is very important. I'm not trying to make the error go to 0 at all here. I'm not trying to reject disturbances or something like this. This is how this is the impedance controller, way of thinking. Interaction is different from, just disturbance rejection. This is very important. And this is the last video. I told you it's not passive, but what does passivity mean? So passivity is different from stability. Okay. So passivity implies stability. And if you have something that's stable, okay, let me stop here. So this is the variable impedance control. It's trying to push, on the wall. What happens if the wall is not there? If the wall is not there, what happens? Imagine the situation. So why is that?
If it was pushing and something got, then like you have a momentum.
It's not about the momentum, because if you go back to the previous, watch the video again. So initially we were telling it to push with, I think it was like something like 3 Newtons or 4 Newtons. Okay, so it's pushing, it's regulating the force, and suddenly the environment is not there. What happens to the stiffness modulation, the variable spring? I keep on increasing the gain of it until what? So I'm trying to push. I'm trying to push further. I'm telling it push harder, and there's nothing to push at. So what happens? It keeps on increasing the stiffness. It feels that I'm not pushing, strong enough, so I need to increase the stiffness, and then make it harder and harder and harder until you hit what? The limit of the actuator, and then you just become unstable. So this is a typical example what the loss of passivity means. So a loss of passivity means here that I'm not guaranteed that if the environment is there, I'm gonna be still stable. But even if what happens if the environment is not there? This is a typical example that you really see that the standard way of thinking about range and pose separately, doesn't work. You have to think of them both together. You need to think of that there's a relation between both.
I need to close the relation between both. I need to always make the behavior depending on the relation between both. And this is why just doing passivity doesn't work usually in practice, okay? First of all, it's very limiting, to always make sure that I'm passive. And if you lose the passivity, for example, like with the variable impedance controller, you need to think of something else, okay? The environment itself, I cannot always make an assumption on, even the passivity assumption, even if it's there, the environment can just disappear, this situation happens. And this is why you need something extra, okay? And this is the new paradigm that we introduced in our work, and it was called energy-aware impedance control. Whenever you say energy, what do you think of? Of course, Port-Hamiltonian framework, right? So everything will be visible in the Port-Hamiltonian. We're not just going to add a spring and a damper for the controller. We're going to add more stuff, something next time I'm going to be telling you about, inshallah, something called energy tanks, okay? So next time, inshallah, the last part was very fast. I'm going to go over it again, inshallah, with more details. I'm going to tell you, inshallah, more about energy tanks. Yes.
If I give the drone desired position and desired range,
Yes.
and it couldn't achieve the desired position,
Yeah.
will this affect the range regulation?
With this controller, you mean?
Yes, if I can control I give the drone the desired desired reference frame
Okay.
and desired range. I want the drone to push at the center of this frame with for example, 5 Newton.
Okay. Yeah.
But I couldn't achieve that position.
I was not there in the beginning, you mean? That's exactly what we have here.
There is some constraints or something prevent me from to achieve that.
That's exactly what you see in the video. So I have this desired frame in this figure, I say go there. And usually have an environment in between. And you're pushing. So you already have contact. You already have a contact force. It's not just the one that you want. So what do? Just increase the stiffness. That's it. And then until the force that you're already pushing with, it becomes the one that you want. That's the idea. So there is no force control alone and position control alone. Again, this is exactly what I'm saying. Don't think of it like this. It's not control of one and the other. It's controlling the behavior between both. You have to always think about what is the relation between the twist and the wrench that this controller is doing. This is the same. This is the philosophy of the impedance controller. Okay. Yes. When we do the modulation of the spring, yes. Not just about the interaction. It's just because we have a variable spring now. This is what loses passivity.
The system now is supplying some sort of energy.
Yes, because of the changing of the stiffness. Yes. It's hard. It's power. Okay. If you go back to the bond graph, you can rewrite it as some sort of that we have a stiffness. I have a spring. I have a spring that has variable k, so the k now is time varying, so it becomes actually as a state, not just a constant. So I need to provide k dot. Where does the k dot come from? It comes from some sort of signal processing algorithm that does some PI controller on the force or on the wrench. So all of these blocks that you see here, okay, they are actually signal processing. So everything that you see here in circles was a physical system, was something that is changing the energy. Sorry, it keeps on changing because of some time transitioning, but the stiffness modulation here is an algorithm that provides the k dot. And when you're doing the energy analysis, you're going to find that when you have a variable spring, you're going to find that the total energy of the system has some extra thing now that has k dot into it. And k dot can be positive or negative. The term that involves k dot can be a positive or negative. So I cannot always guarantee it's passive. Otherwise, I'm not going to be able to do the wrench regulation that I want. So that's the thing. So here, this is an example of a non-passive control. Okay. But the fact that the drone, just fell, during this behavior is not because of it's non-passive. Don't get me wrong. It's because of in the environment itself, some stuff I cannot model. Even if I assume that the environment is passive, it can just disappear. I can always have this situation. For example, Sajid now is working on something in his thesis, for example, that is dealing, for example, with valves. Maybe, I don't know if he's changed his mind or not, but maybe he's working on it. Still working on it. That if you have a valve, what happens when you have a valve and you start to open it? at the beginning, you're just applying too much force, and what happens after that? It just, you go into a situation where the stiction, just disappears. So this is an exact situation where you can have you're applying a torque, and after you're applying this torque, you find that, let me just close this. After you apply the torque, you find that, it just disappeared. I don't need it because of the environment itself is unpredictable. So it's not about modeling the environment. You cannot model the environment. If you say it's passive, you can do it on paper, but it's not how in real life it works. Even if you have passivity, it can still, break because the environment, you can have unpredictability. You cannot model, you cannot say anything about it. You need to be prepared for it with the control. Sorry? These are unpredictability of the environment. We need to make sure that the controller itself has some sort of way that can think about the environment without modeling it. And this is where energy tanks come into place. So energy tanks will be able to give the controller, or in this case, the closed loop system, a way to try to see what the environment is doing without actually knowing or without seeing the environment. It's like internally trying to calculate what the environment is doing. And this is exactly what will be energy tanks. So energy tanks will do this for us. Okay? Yes.
The system as is passive. I mean, because
Yes. Yeah. No, the non-passivity is because of the controller. So with the standard impedance controller, you have that the controller and the system and the drone. By drone here, I mean just the rigid body. So the rigid body of the drone and the controller of the drone and the environment, they're all passive, which means I have guaranteed stability, provided that the wall is there. When I had the variable impedance controller, the controller itself was not passive. So the controller part was not passive. In the robot itself part, which is the rigid body part, was passive because I canceled the gravity. And then I was left with the environment. It was also passive, but the closed loop system was not passive. But this is not why it broke. It broke because the environment just disappeared. So it has nothing to do with passivity itself. Okay. And I'm going to show you actually in the next time with energy tanks, you can always trick passivity. And it will not be clear now what I mean here. But passivity is just, it's a theoretical concept. It's really something we can do on paper. And it will show you really the limitation of just doing Lyapunov analysis and, trying to do math to see what the real life is working. Real life is different. Real life, you have unpredictability, you have things that are dynamic, you have things that are, disappearing, interaction, we have all this. And you have to be very natural. We as humans, we do this interaction very naturally. So how can we put this in the robot? This is the topic of next time, inshallah. Yes.
Just confirm. So what you just mentioned now, sir, the last controller is not passive.
Variable impedance control, you mean? Yes.
But then the whole system is stable.
No, you have no guarantee. So what do you mean by stability?
At that part, before the environment was taken away.
It was not stable. It was not guaranteed to be stable. That's the thing. In the video, it was stable, but we did not have a theoretical proof. We do not have a theoretical proof that changing the stiffness will guarantee that for any environment, and that's the thing, for any passive environment, I have stability. Maybe for some environments, I do have stability, for some not. And this is something actually I haven't seen so far. And it's very interesting really to see it in research. How can you build, a small setup to show that, this is interacting with the environment. Okay, this is a robot interacting with the environment. And I have a passive controller and a non-passive controller. You show that with the passive controller, I am stable. With the non-passive controller, I'm unstable with the same environment. I haven't seen something like this before. These are all theoretical results. There is actually some proofs that if I have a non-passive controller, you can make up, there exists, so there exists some environment that could be, that's passive, that can make the non-passive controller unstable. This is excellent, theoretical research. I'm actually thinking about it. Something. So actually, if something, I know you're all busy, but if maybe someone in the future can work on it, but it would be excellent to really show it. This is so far as theoretical results. Yes. Yes. Yes.
Then it can be non-passive and cannot guarantee context stability.
So with the I think yes. So because the only thing, so impedance means inertia, stiffness, and damping. The only thing that you can make time varying, it will not change the passivity, is the damping. You can make the damping time varying. You know, actually, if you remember, we had this damping part that was nonlinear. I could have actually removed this nonlinear damping by adding, negative nonlinear damping in the controller, and it would still be passive. So it will not change anything. The only problem is if you change the stiffness, you're changing the potential energy. If you change the desired inertia, you're changing the kinetic energy. And then you have non-passivity. Yes, you lose the passivity in both cases. That's correct.
So just to confirm finally, passivity implies stability.
Yes.
But we could have,
if you have a passive environment.
if we have a passive environment,
Yes.
or we could have a setup where the controller itself is not passive.
Yes.
But the whole setup or environment combined together appears to be somewhat stable.
Yes, of course. But, and this is again what I hope to show someday, that can we build up an environment and two controllers, So a robot arm, just a Franca, and you have an End-Effector, and it's dealing with on the other side an environment. This environment, of course, you don't think of it as just a simple environment. It has to be something very complicated, So actually, I'm thinking of using another robot to represent the environment on the other side. Actually, some people, for example, that are working in space robotics, Pansy, for example, she's doing something there, and to represent, a space robot, they put the robot arm on another robot arm that compensates for gravity. It makes it like zero gravity. So the other robot arm is behaving as if it's you're floating in space. The same idea. You can use a robot arm as the environment, and then you're going to have your own robot with the controller, and it would be either to show that a passive controller dealing with this passive environment, okay, is stable. A non-passive controller dealing with the same environment is unstable. Of course, this environment itself has to be handcrafted. We need to make it very complicated, very nonlinear, in such a way that we really show that it is possible. Just a wall, there's not a lot of dynamics. It's really not moving. For example, if you have 3 branches, this is already a dynamic environment. It has dynamic of its own. For example, if you're trying to do crop harvesting, with a robot and so on.
So with this setup,
I'll stop here because I see that, okay, we took much time. So if you have any questions, I can take them. But just for everyone else, if you're already bored enough, I'll stop here. جزاكم الله خير, and see you inshallah next lecture on Tuesday. Right? Okay, جزاكم الله خير.